In the series of lectures on miscellaneous topic, I will be dealing today electric resistance heating. You know, conversion of electrical energy to heat energy is a very clean form of energy. I have thought to include this topic because many students of undergraduate metallurgical discipline or in any area for various their laboratory work, for their project work, for their thesis work, they may be requiring to design a furnace. In many instances, for laboratory work, the furnace as required by an experiment may not be ready-made available in the market. So, one has to design the furnace depending on the requirement. So, it is with this objective I thought to include this particular topic, and today I will be addressing on electrical resistance heating, and if the time permits I will also like to tell you how to design and construct a furnace. Now, you know, we all of us know when a current flows through a material of certain resistance, heat energy is produced. That is, we know all of it. The object can be heated indirectly or can be heated directly by way of electrical energy. Example of direct heating, you must be knowing electric arc furnace. The direct heating, you create an arc between anode and cathode and heating is transmitted, that is the electric arc heating. In indirect heating, you have to select a material which is heated, and that heat of the material, it transfers its energy to the object. So, that is why we call what we will be addressing today, that it is the we will be addressing indirect heating. Indirect heating, which I mean that the object is heated by the radiation of the heating element, that is what the indirect heating. Now, it is also clear that this is a very clean form of energy. With the clean form I mean, so far in the fuel fired furnaces in several lectures we have addressed that energy from fuel is derived in the form of products of combustion, and then they give its energy to the object and they exit the furnace. So, it is not a clean form of energy. In that respect, electrical energy is a very clean form of energy. Now, the principle of electric heating, it can be enunciated in the following way. Say, suppose R is the resistance of the material, R is resistance of material and I is the current flowing for unit time, current flowing in a material for, let us say, time t. Then heat produced H, that is equal to I square R and T joules. Let us say T is the time. Now, we know power dissipated, that is equal to P, and that is equal to I square into R. That will be in watts. Now, we know Ohm's law. Now, this Ohm's law states that V, that is equal to I into R. So, we can get now power P that is equal to V square upon R square into R, that is equal to V square upon R, where V is the voltage across the heating element, across the heating element. So, that is how, for the calculation purposes of how much watts, voltage difference R and I, they are connected, and that is where one can calculate the so called power. Now, what are the requirements of heating element? Now, so far we know that when a current is passed through a material of resistance R, heating is produced and heat energy is produced. And we can quantify by P is equal to V into I, that is the power that is obtained when a voltage difference across the heating element is produced. Now, so what are the requirements for heating element? Requirements of heating element. Now, I am using the term heating element because they are again the materials, and since they are used for heating, so we call them heating element. They are also, in fact, they are the materials, they are used for heating, that is why we call them as a heating element. So, the first requirement is that the material should have high melting point, should have high melting point. That is the first requirement. Of course, the melting point of the material should be much higher than the temperature to which the object is to be heated. That is very important thing. Second is that stability in atmosphere. Stability in atmosphere. With that, say you are employing the heating element, say under endothermic atmosphere or exothermic atmosphere or reducing atmosphere, then the material should be stable against corrosion and chemical reaction with the atmosphere. Because you have seen in the earlier lecture, the furnaces employ different types of atmosphere. So, in selecting the material for heating element, a precaution is to be taken that the selected heating element, it is inert to the atmosphere which is chosen for heating. Second important point. Third important point is resistance to thermal and mechanical shock. Resistance to thermal and mechanical shocks. Because many times when the furnaces are heated up, you pass a large amount of current through the heating element, then you decrease the amount of current depending on the temperature that is required. So, those thermal gradients, the heating element should be able to sustain those thermal gradients and also mechanically induced forces, so that it should not crack or it should not be, it should be remain stable. Fourth important point is resistivity. In fact, resistivity is the ability of a material to inhibit the flow of current in presence of an applied voltage. That means, if your larger is the resistivity, more will be the heating, because it inhibits the flow of current and accordingly large amount of heat will be produced. So, these are some of the requirements. Of course, if you have many, you can include more, some of the important which I have listed over here. Now, considering this, what are the available to us? So, the available materials, say, 1 is the metallic alloys. metallic alloys, and these alloys are based on say system iron, chromium and aluminum. You know, this is the, all of you are aware, this iron, chromium, aluminum, they are called the Canthal wires. Another is the nickel, chromium and iron, and you know they are all the nichrome wires. These names you must have heard. Second available material, they are the refractory metals. Refractory metals, say for example tungsten, molybdenum and tantalum. They are very high melting point and they can also be used for heating element. Third is noble metals and alloys. Noble metals and alloys, and in this case platinum or platinum rhodium, they are also used to construct a furnace, although they will be very expensive because they are, the platinum wire is also a very expensive thing. Another type of heating element, they are the non-metallic heating element. Non-metallic heating element, and under non-metallic, the one of the most important that all of you know is also that is the silicon carbide. Another important is the molybdenum disilicide. So, these are the materials which are available for high temperature indirect heating applications. Now, let us see a little bit the design of metallic element. Design of metallic elements. Metallic. Now, for example, let us consider a wire, say example this, the wire, and this wire, let us say this is the diameter of the wire, this is the diameter of wire, let us say its diameter is equal to d. If L is the length of wire, L is length of wire, this is the resistivity of the wire, resistivity of wire in ohm centimeter, and V is the voltage across the wire, voltage across the wire, I is current, and R is the wire resistance. Wire resistance, so that we give in ohm, that is say in ampere, and that is say volt. Then we know power, that is equal to I square into R, and R is equal to resistivity 4L upon pi d square in ohm, that is for circular cross section wire, for wire of circular cross section, circular cross section. Now, say surface area of wire, say surface area of wire A, that is equal to pi d into L, that is in centimeter square. Therefore, we say watt, that is power radiated per unit area, power radiated per unit area, that will be equal to P upon A, and the dimensions are watt per centimeter square. This is a very important component of the design of the furnace using metallic element. You must know what is the power radiated per unit area, that is the watt per centimeter square, so that the wire can sustain the flow of current. Now, this power radiated per unit area for heating element, say power radiated, that is watt per centimeter square. In fact, that is the important part for design of the furnace. You must see that most of the power radiated by the wire is available to the work, because more the power available from the heating element to the work will be heated up faster. What I mean to say is that when these heating elements are installed in the furnace, you pass the, you rather apply the volt, current will be produced, wire will be heated up, and it is the radiation of the wire that transfers the heat to the surrounding, and the surrounding consists of the object as well as lining walls. So, your objective should be that the maximum amount of heat should strike the object and less fraction should strike the lining. That means, power radiated, the fraction will strike the object, fraction will strike object, and the fraction will strike the lining. Fraction will strike lining. Of course, from the lining these will be reflected, absorbed, and the losses, all these things are associated. So, what I mean that the radiation of the heating element, it should be maximized, so that maximum amount of heat is strikes the object. That means, the heating element should be inserted in the furnace such that the object gets maximum amount of radiation. Now, here the shape of the heating element, support will affect also the heat transfer. Say for example, imagine the heating element, they are freely suspended, then the heat transfer will occur in all directions. If they are supported in groove, then the heat transfer will occur through the groove. So, what I mean, these are the say methods of arranging the heating element in a furnace. Now, say maximum power transfer, say W, that is equal to sigma 0 1 upon epsilon h plus 1 upon epsilon 0 minus 1 Th4 minus T0 to the power 4, that is watt per meter square, where epsilon h is the emissivity of heating element, epsilon 0 emissivity of object emissivity, Th is the temperature of heating element, T of heating element, and T0 is the temperature of object. So, this is the maximum power that is available. However, this equation does not consider the losses through the lining, and these things are not in the equation. And what this equation says, that is the maximum amount of power is available. Now, once power is known, then we can calculate surface loading is important. Then we have to select wire of appropriate size and area. Service life of the wire is also very important. In fact, the surface loading of the wire is many times specified by the manufacturer. That means, how much amount of load the wire can sustain, that is specified by the manufacturer. So, those informations are to be collected. Now, certain say important certain important heating element, certain important heating elements. Say we take, say for example, nickel chrome. Nickel chrome. Now, nickel chrome, it has chromium, and chromium on heating forms Cr2O3, and that protects the that protects the wire against further oxidation. Where Cr2O3 is stable and the material is prevented from further oxidation. Similarly, the compositions are, say you have 20% chromium, 80% nickel, or 15 chromium, 25 iron and 60 nickel. All these different types of materials are available, and they can be used maximum up to 1200 degrees Celsius. Another type of is say iron chrome aluminum, iron chrome Al, that is all of us know, they are the Canthal wires. Now, here the aluminum, it forms Al2O3 and further oxidation is protected. Say for example, 22 chromium, 5.8 aluminum and rest iron, that is called Canthal A1. Now, there are different grades of Canthal wire is available, and that can sustain temperature up to 1400 degrees Celsius. Then you have say 22 chromium, 5.3 aluminum plus iron rest, this is Canthal A. That can go up to 1400, however, recommended is 1300 degrees Celsius. Another grade, say 22 chromium, 4.8 aluminum plus iron, this is called Canthal D, 1300, but the recommended is 1200 degrees Celsius. Now, here they are available in rod form, wire or strip size. All shapes also are important. Another, say we have refractory metals. Refractory metals, we have molybdenum, and molybdenum melting point is 2630 degrees Celsius, that is its melting point. It can be used safely from 2000 to 2500 degrees Celsius, that is used in this particular range, available in wire, rod or in sheet form. Now, this molybdenum heating element can be used safely in say hydrogen atmosphere or in cracked ammonia atmosphere, cracked NH3 atmosphere. Another important, we have a tungsten heating element. Its melting point is 3380 degrees Celsius. It can be used safely up to 3000 degrees Celsius, and it is also available in the form of wire, rod and sheet. It is specifically used for in the atmosphere dry hydrogen and vacuum up to 2400 degrees Celsius. Then we have say noble metals as the heating element, and under noble metals we have pure platinum or platinum 10% rhodium or platinum 40% rhodium. These are the available. Now, the melting point of all of them here is 1768 degrees Celsius, 1825 degrees Celsius and 1900 degrees Celsius. Now, useful temperature, it can be applied safely up to 1400, 1550 degrees Celsius and 1725 degrees Celsius. They are also available wire, rod, strip form, and they can be used in oxidation atmosphere. Oxidation atmosphere. Under non-metallic element category, one we have say molybdenum disilicide, that is also called Kenthal, ST super. There are here different grades are also available. It can be used safely up to 1700 to 1800 degrees Celsius. However, in air it can be used up to 1700 degrees Celsius, under inert atmosphere 1600 degrees Celsius, and reducing can be used maximum up to 1400 degrees Celsius. Another important heating element is silicon carbide. Now, silicon carbide it can be used up to 1540 degrees Celsius. It is good for hydrogen and reducing agent. So, these are the certain heating elements. Now, say silicon carbide rods, they have two distinct zones. There is a heating zone, and that heating zone is a very important thing. That is the central portion of the rod is the most probably heating zone, and then they are supporting zones. Molybdenum disilicide heating element, they are brittle and careful handling is needed. Now, suppose say now having given this idea about the different heating elements, their service condition, temperature limitation and so on. Now, selection of heating element for furnaces. The selection of heating elements for furnaces. So, here some of the important criteria. Say one criteria is what is the maximum element temperature, let us say MET of the heating element. Now, for that I am selecting three different type of heating element that I am putting it over here. Say for example, here I take metallic heating element, this is metallic, this is silicon carbide and this is MoSiO2. So, I am comparing now these three heating elements for the selection purposes. So, the metallic elements, they can be used say this temperature is around 1425 degrees Celsius and this temperature is around 1100 degrees Celsius. So, this area represent maximum element temperature, and this thing is the useful limit. Now, similarly, if I consider silicon carbide, then for silicon carbide, this is for the silicon carbide, and silicon carbide it can be safely used up to 1520 degrees Celsius, whereas the maximum element temperature this is the 1650 degrees Celsius. Then if I take molybdenum disilicide, then this temperature is around 1700 degrees Celsius and this temperature is around 1820 degrees Celsius. So, this is the information about the maximum element temperature, that is one thing we require. Now, their response to the atmosphere will also be different. So, let us consider now say maximum element temperature for metallic elements for metallic elements in different atmospheres. In different atmospheres. Again, I will plot, say here, I taken two heating element. One is the nickel chromium, that is nichrome, and another is a canthal. So, under vacuum, say under vacuum, this one, say this one is in fact nickel chromium, whereas this one is the canthal. So, what I am comparing nickel chromium versus canthal, for example, in vacuum atmosphere. In atmosphere is vacuum. So, nickel chromium can be used, this is 1000 degrees Celsius and this goes up to 1200 degrees Celsius. So, canthal in fact is represented by this, and nickel chrome I will be representing by this particular line. Now, similarly, for example, if I take now under nitrogen atmosphere, I take nitrogen atmosphere, and for nitrogen atmosphere, say both the elements, they can be used safely up to 1200 degrees Celsius. This is again nickel chrome, and this temperature is 1250 degrees Celsius. If I take for example hydrogen atmosphere, this I take hydrogen atmosphere, then under hydrogen atmosphere, this is for the nickel chrome and this is for the canthal. So, this one is for nickel chrome and the temperature for this is 1250 degrees Celsius, whereas canthal can be safely used up to 1400 degrees Celsius. Similarly, the response of other element can also be determined in order to select a heating element for a particular application. So, the fundamental operation limitations are fundamental operation limits or operational limitation. Number 1, maximum element temperature. Now, maximum element temperature should be greater than the temperature required or than the temperature of the furnace. Second, maximum specific power loading. Maximum specific power loading of the element, that is in watt per centimeter square. That will decide the watt loading. And third important thing is that shape of the element. What shape you are going to select? Shape of the element. Now, element, then shape of the element, element support system, element support, then response of element against external forces, for example, mechanical or thermal or electromagnetic and so on and so forth. So, these are the operational limitations. Now, for example, now since maximum element temperature will always be greater then furnace temperature, then and if you consider those two figures, then the following conclusion emerges. One, say if maximum furnace temperature, I will call this MFT, if maximum furnace temperature for example is less than 1425 degrees Celsius, then all three type of elements, nichrome, molybdenum disilicide and silicon carbide can be used. The application will only depend upon the economic considerations, because silicon carbide and molybdenum disilicide, they are expensive. Second, if MFT or maximum furnace temperature is in between 1425 to 1650 degrees Celsius, then only silicon carbide and MOSI2 can be used, if you see the previous figures. Third, if say maximum furnace temperature is greater than 1650 degrees Celsius, then only molybdenum disilicide is a possibility, no other heating element can be used. So, the choice of course depends upon what is the maximum furnace temperature is required. In addition to this, metallic wires are available both in wire and strip form. Metallic wires can be operated with the line voltage, but silicon carbide and molybdenum disilicide heating element, it cannot be operated with line voltage. For that, you require the so called transformers. So, of course, these are the some considerations for selection of the heating element. Now, say some of the advantages of heating element, advantages and disadvantages. Say for example, I take first metallic elements. Say some of the advantages of metallic elements. One, they are available in wire and strip form. It can be fabricated with the conventional metal forming techniques into a variety of shapes and size. Second, heating system can be worked with the line voltage. They are less expensive than SiC and molybdenum disilicide heating element. These are the advantages. Now, under disadvantages, say one of the main disadvantages is their low maximum element temperature, not self supporting, they require a support, say not self supporting. Their resistance also increases with time due to reduction in cross section by oxidation and elongation, resulting in decreased power output and eventual failure. These are certain advantages. One is to compromise between these two things. Now, if we take say silicon carbide heating element, now silicon carbide heating element, their advantage, again they are available in all sizes and shapes. All sizes and shapes they are available. They are self supporting. Then higher temperatures are capable of operating at higher temperature, and another important, relatively easy to change when the furnace is hot. So, that is also can be considered as an advantage. Now, under the disadvantages of silicon carbide heating element, the disadvantages, few disadvantages are, say they are ceramic material, therefore risk of failure. They are very brittle, So, risk of failure is one particular disadvantage. Second disadvantage is, say you require transformer to operate them, and third, electrical resistance also increases with time, that is aging, meaning more maintenance attention is required. So, these are certain advantages and disadvantages, there are certain disadvantages of this. Another, say molybdenum disilicide, advantages, again available in variety of size and shapes, almost all sizes and shapes are available. Most important advantages is that they can be operated, their maximum element temperature is very high, that is very high, very high element temperature is there, and as a consequence the furnace can be operated at high temperature. Third, say stable resistance, that is old and new molybdenum disilicide element can be joined in series. Fourth, longest inherent life of all thermal elements. And fifth advantage is fast thermal cycling is possible without element degradation, that is you can apply a fast heating cycle without degradation of the material. Now, under the category of disadvantages, that is again this is ceramic material, risk of failure. Second, you require transformer. Just with the line voltage, these molybdenum disilicide material cannot be operated. And third, it is the most expensive. It is most expensive under the heating element which we have considered. Now, in brief, I will like to illustrate you, say what is required when you want to design a furnace. Now, for example, for designing a furnace, a laboratory type of furnace, designing a furnace, what is required. Now, for example, I take a ceramic tube, whose outer diameter, this is the outer diameter, and let us take this ceramic tube is 40 centimeter long and its outer diameter is 5 centimeter. We want to design this furnace to operate at 1000 degrees Celsius, operated at 220 volt line, and the line has 5 ampere current socket. This is what is given to us, how to go ahead for this. So, first of all we calculate the power, that is power will be 220 into 5, that will be approximately I will say 1 kilowatt. Now, I can calculate say R resistance, that will be equal to 220 upon 5, that will be 44. So, I am taking approximately 40 ohm. That is, I have to design the furnace for 40 ohm resistance. So, now I will go for selection of the wire. So, that will be the now my specification for design of the furnace. The furnace will consist of 1 kilowatt. The resistance of the furnace will be 40, approximately 40. Now, I have to select the wire so that I can meet this specification in order to create a temperature of 1000 degrees Celsius. Now, what is done? So, now I calculated the ohms that is required for design of the furnace. What I have to do now? I have to select the length of the wire, right, and then the number of turns. So, what I do now, I select the wire. So, I have put here wire diameter, say in D, which is in millimeter, then resistance of the wire, that is in ohm per meter. Then you must also know current capacity. Now, current capacity of the wire should not be less than 5 ampere, because 5 ampere is the design value, the wire will burn. It should be more than 5 ampere. Now, wire length and number of windings that is required. Number of windings you can calculate pi d, that is the circumference. So, you can calculate that. So, I select the wire, for example, one is 1.60 millimeter. The resistance is given 0.691, current capacity is 10 ampere, that falls within my region of 5 ampere, and the wire length, it comes say 40 divided by 0.691, that is 58 meter, and if I use this wire, then I have to have approximately 369 windings on this particular tube, that is 5 centimeter diameter. That may not be possible. So, I go to the next wire, I take now 1 millimeter, its resistance is 1.77, its current capacity is 9 ampere, wire length is 23 meter, and I get number of windings 144. For discussion, I am taking another wire of 0.7 millimeter, 3.61 and 7 ampere, number of windings, wire length is 11.1 meter and number of windings is 71. So, now I have to plan how I am going to wind this wire. So, now let us see. So, I take, this is a tube, 40 centimeter. Well, I have to leave somewhere here 2 centimeter on this side, 2 centimeter on this side. What for? That is one that will be going out of the your say furnace. So, the winding length is approximately, let us say 36 centimeter. Number of winding corresponding to 369 is not possible in this particular length of the furnace. So, we go to next 144 number of winding. So, I divide minus, for example, in 4 parts, 1, 2, 3, so 9 centimeter, 9 centimeter, 9 centimeter and 9 centimeter. Now, per say in each 9 centimeter, I have here 36 winding, here 36 winding, here 36 winding, here 36 winding, I can do that. Now, one of the important message that I want to give you when you want to design a furnace, see that the ends of the furnace, they are thickly wound as compared to middle of the furnace. Why? Because those ends will be heated at higher temperature. So, heat transfer will occur from end to the middle part, so that you can get a uniform temperature zone within the center part of the furnace. So, with this objective, what we do is that in the end portion we take 40 windings here, here also we take 40 windings here. So, we get here 32 windings now and 32 windings now, and that can be very easily compensated in a length of 36 centimeter. So, that is how I thought to illustrate how to design a furnace, because many times you may be doing your BTech project or whatever you will be doing, you may be designing a furnace, or you are, because those specifications may not be available for whatever the reason, maybe this can help you. It is because of this I put it here. Now, at the end of the lecture, I will like to give you some of the self-assessment questions. Self-assessment questions on miscellaneous topics. Now, the first, say, what is the principle of measurement of temperature? What is the principle of measurement of temperature? I discussed those things in the lecture. So, you can make the appropriate answer. Briefly describe the different types of thermocouples. The different types of thermocouples. That's also I given, and you can see that you update your. Second, discuss the objectives of different atmospheres in high temperature furnaces, Now, in your discussion you can also include the objective of the furnace. For example, you are writing for anneal the material or quench the material or sinter the material. So, depending on the objective, you can discuss the type of atmosphere that is needed to perform that metallurgical function. Third question that I will like to give you, name along with applications the different types of atmosphere. Now, what I want here is that in fact, what are the different atmosphere, and if you can add a line how these atmospheres are created and what are the important requisites. For example, in endothermic atmosphere, we use air less than stoichiometric amount, so extra amount of heat is required. That is what, in fact, if you include those things also here, you get update knowledge of the various atmosphere for high temperature purposes. Fourth, discuss the principle of radiation pyrometer. Discuss the principle of a radiation pyrometer, mention the requirements to design a radiation pyrometer. Now, with this I mean, because pyrometer has two essential components, as I illustrated in my lecture. The important is the sensor to detect and the electronic circuit, and all these requirements you should include over here. Now, the next question that I want to give is rather fifth one. What is the principle of electric resistance heating? What is the principle of electric resistance heating? The sixth question that I would like to give you, discuss the advantages and disadvantages of the following heating elements. One, take metallic one. Say under metallic, I mean nickel, chromium and canthal wire. These are the things under consideration. Second, silicon carbide, and third is the molybdenum disilicide.